Hi, everybody. My name is David Hendricks, and joining me today is Philip Deppenwiese from 9-Element Cybersecurity.
Hey.
Today, we are going to talk about firmware security without obscurity. Here's a quick overview of our agenda for today. We'll start by talking about some principles of secure firmware. Then we'll talk a little bit about the firmware ecosystem. So we'll talk about the boot flow, our implementation, the system transparency project, and then we'll finish things off with a demo and a call to action. So let's jump right into it. So, principles. The first principle we'll talk about is reducing your trusted computing base. What's a trusted computing base? Well, that's technical jargon for all the stuff that goes into your software, and in our case, the firmware. We want to minimize what's necessary, strip it down as much as we can, and eliminate any unknowns as possible. Firmware, as many of you watching this know, is very complex these days, with a size and scope that actually rivals some simple operating systems. It used to be that a PC or server BIOS could fit into a few kilobytes. A good example is the PC Engine's Tiny BIOS, which you can download, and it's about 10,000 lines of assembly. Which, it's a fair bit of assembly, but it's small enough that one person can write it and maintain it. Nowadays, we don't even call it BIOS, we call it system firmware, since it does a whole lot more than BIOS has traditionally done. And it's usually in the millions of lines of code and often takes several megabytes. Firmware, of course, initializes the hardware and loads the operating system. And in order to load the operating system, it might need storage drivers, file system drivers. If you're net booting, it needs networking drivers. It needs a networking stack, so IPv4 and IPv6 support, or potentially other protocols. If you want to present a menu to the user, you might have a graphics driver. You might have input devices such as USB keyboard support and many other things. And while this is all necessary to support modern hardware and use cases, it creates a large attack surface in code that is usually proprietary, opaque, and not heavily scrutinized. So our second principle is that we need to know what goes into firmware. We want it to be auditable, so preferably it should be in source code format, but even if there's binaries such as the management engine or platform security processors, we need to know what those are doing. We need to know what their firmware does and make sure it's not doing anything it shouldn't do. And for the host firmware, as you may have seen from some of the Linux boot presentations, a modern server UE5 firmware can have hundreds of drivers. These are Dixie modules that are described in the Linux boot presentations. And we want firmware to be accountable. And by this, I mean we want to be able to account for all the changes that have gone in, preferably using a source code management history such as a Git log. Next, we want firmware to show provenance. So typically when you download firmware or some other binaries from the internet, you should try to compare it with a checksum like a SHA-256 that's provided by whoever is hosting the binary. And this is good because it helps make sure that the binary is not corrupted, and it gives you some assurance of that you're running what you think it should be. However, it doesn't tell you anything about who created the binary and how. So I highly recommend reading the Firmware Security Best Practices document from our friends in the OOCP Security Working Group. A couple items they outline for the role of a signature is things like the build and signing process must be auditable. The environments, tool chains, and other inputs that themselves have known provenance and the people or role accounts used to execute the build are recorded as part of that process. And the mapping of inputs through the build process to the outputs must be deterministic and reproducible. So we want to be sure that the binary that we receive, not only does it match the checksum or the hash, but also that we have a good idea of who made the firmware and how. So with all this in mind, the user should be able to validate the integrity of the firmware image and know what they're running and who created it. And of course, they must be able to build it themselves, because of course, who can you trust more than yourself? So that all sounds good, but how does it apply to the industry as a whole? So let's take a look at the firmware ecosystem. Traditionally, firmware changes hands multiple times before it reaches the customer. And here's an overview of how the firmware fits into the supply chain, starting with the silicon vendor and ending with the customer. Firmware enters at the very beginning of the process with the silicon vendor, And in fact, they're probably reusing code that's been modified from previous generations of their products. They'll hand the reference code and documentation and other collaterals to partners such as independent BIOS vendors or IBVs, OEMs, and ODMs. IBVs will integrate the reference code into their framework and add additional features. ODMs typically work on the hardware design based off the silicon vendor's reference boards and will usually license firmware from an IBV. And then the OEM, who's going to create a product, uses the partners with the ODMs to take that product, wrap it in plastic, maybe add some more features such as a boot splash screen with their logo or something, and additional features. And then the OEM will sell the product to the customer who isn't really supposed to know what firmware does or where it came from. Now, that's basically how the industry has been since the 80s, but along came a special kind of customer, the hyperscaler. And hyperscalers turn this model on its side and are vertically integrated. Unlike most customers, they're involved with every step of the supply chain and work closely with silicon vendors and hardware manufacturers. Hyperscalers source components, design boards, take delivery of racks, provision them into the fleet, maintain and repair them, and eventually decommission them. So instead of seeing a firmware at the end of the process, hyperscalers see it throughout the entire process. So when a machine is finally decommissioned, they must also ensure that any potentially sensitive data, including signing keys, are completely wiped out. And then this gets into the circular economy where there might be a secondary or tertiary owner of the machine. So for hyperscalers, accountability is important for firmware. They need to know everything that goes into it, what it does, where it came from, and how to verify the integrity of it. And of course, they need to make sure that nothing sensitive can get leaked, either during runtime or decommissioning. So how do we achieve that? Well, here's Philip Deppenwiese to give you some details.
Yeah, thanks, David. Yeah, first of all, let's grab the evil at the root. The biggest problem at the moment with the firmware is the firmware growth. So 20 years ago, the firmware was really small. It was probably 128 kilobytes big, but nowadays it's 160 megabytes big. And this comes from the BIOS, which is 32 megabytes, and the BMC firmware, which is 128 megabytes. And we think that also in the future, the firmware will grow, and there will be also more and more components having firmware on it. And so in around 10 years, probably we have 1 gigabyte of firmware, which is not firmware anymore. It's more like an operating system. And this gives us problems because firmware is huge and the trusted computing space base should be small in terms of security. If we look at the hyperscalers boot flow, we have 4 firmware components, or let's say software components, mainly on the hardware platform itself. We have the BMC, which is started first, and the BIOS, the bootloader, and the operating system. In the real world, it looks a little bit different. So it's not really colorful. It looks black because they're all a black box except the operating system. So we have closed source BMC firmware, we have closed source BIOS, and often the bootloader itself is also closed source. This is really not open, or you can't audit it, and it's hard to verify where it comes from. And in order to solve that, we are working in open system firmware to get rid of the black boxes and create open source, or let's say bring open source firmware on the parts BIOS and bootloader. You can see that here we have the Open BMC firmware itself. This is not part of open system firmware, but it's given. And we also have, for example, in the open system firmware bootflow core boot and min platform. We have a Linux boot and Tiano Core as bootloader. And you can, whatever you want to use, it's all open source. You can flexibly choose from it. For our implementation we did for Facebook, on OOCP hardware, we use Coreboot as open source firmware. It's a 20-year-old open source firmware, which is compatible with Intel FSP and AMD AGESA. It works on a large variety of hardware, and it has a really small TCB, which is really good for security. It also supports runtime services, and it can load a Linux operating system as part of the firmware, which means it supports Linux boot. You can also just use any other bootloader like Core. One important part of the security is the measured and verified boot through the firmware. For core boot, we support a small root of trust, 4 kilobytes big. It is write protected often. We have a measured boot with a TPM. We support verified boot, which is similar to UEFI secure boot. And core boot support reproducible builds, which means it's perfect for trusted computing applications for remote attestation, for example, and local attestation. For Facebook, we also implemented inter-trusted execution technology as part of the core boot stack. We added memory wiping support in order to wipe credentials from the memory. It's all implemented open source. We do IBB verification, which means we check the 4 kilobytes big first patch, which is loaded off the firmware. And we are also able to set up a dynamic root of trust for measurements, so runtime measurements for the operating system or hypervisor. We also support Linux boot with Intel TXT through tboot hypervisor or trench boot. Yeah, now if we look at Linux boot is a Linux kernel as a bootloader. It's inside the firmware. It has lower privileges as a firmware, and it loads stable kernel drivers and supports a lot of hardware, which is really great. So we don't need to rewrite all drivers. It has high visibility and also runs Golang user space in a DRAMFS, which means we can just write Linux applications inside the firmware. We can boot Linux, Windows 10, and other hypervisors at the moment, and it's easy development. Linux boot is capable of loading operating systems from hard drive with any type of configuration, or just net booting, which is the most interesting part for hyperscalers. So what we can do is we can do HTTPS or HTTP boot. We can do PXE or torrent boot. We support DHCP itself, static IPs, and also any storage device. If you want to have security in your bootloader in Linux boot, we provide you signature verification and a measure boot functionality for TPM, and also secure random runtime. If you look at the QR code, you can find a talk of Ophir Weisse about booting Windows 10 from Linux boot. System transparency puts all those principles David talked about together to one solution. And the idea of it is to provide for production engineers and site reliability engineers systems which are transparent for them, to them. So that they have a whole open source technology stack from the BMC over the BIOS to the bootloader and then to the operating system. And all those components measure hashes into a binary transparency log. And this binary transparency log is an append-only log. It's similar to Let's Encrypt certificates transparency log. And you can see what was launched on the platform itself, which is really great. We have a specification not available yet, but it will come soon. There's a reference implementation in Linux boot called stboot. And we have also system transparency is not only available on open system firmware, it can be used on any UEFI or BIOS legacy system. It's not that great then with experience, but it can be used with it. Now we are coming to our OCP Reg 100S demo. It's OCP hardware with Intel TXT and with open system firmware stack. Yeah. What we now see is the OCP Reg 100S booting up. A second time, first we do a reboot, then we will boot it up. David, can you please scroll a little bit down? Yeah, thank you. Now what we see there is core boot booting up with Intel TXT initializing the hardware, and also Intel TXT initializing the dynamic runtime, the dynamic root of trust for measurements. And then it loads the Linux bootloader, which comes now. And now we're in the Linux kernel. And now we have the Golang bootloader, and the Golang bootloader will run the tboot hypervisor. And after the tboot hypervisor, now we run the tboot hypervisor, it's really fast. We do a getsec as enter, which is an Intel instruction for security. And after that, we have the operating system, which is CentOS in a measured launch environment. That means it started with Intel TXT, it's protected by Intel TXT, and then we will see some PCS. Now tboot launches the operating system. So CentOS, there we go. We are back to the Linux kernel of the operating system. And in a few seconds, we will see the PCR measurements. Sure, we'll just take some time. There we go. We see that PCR 17, 18, and 19 are extended, which is quite good. And that means Intel TXT is launched. We can also see that the TXT measured launch environment is set up and the sequence flags is set. And yeah, that's the demo. Let's go back to the slides.
Okay.
Yeah, let's come to the call to action. Visit us online at the OSF Experience Lab. Check out our community and sub-projects, which are basically the Open System Firmware project itself. For sure, join the mailing list, do that. We have the systemtransparency.org. You can just look there and find some information about the technology I showed you. There's also sub-projects like Core Boot, Linux Boot, and URoot. Talk to the vendors and buy the right hardware. Just go to the OOCP marketplace and find the checkbox for Open System Firmware. If it shows yes, the hardware comes with Open System Firmware. Join us at the Open Source Firmware Conference, OSFC.io, and also at the Open Source Firmware Slack, slack.uro.com. Yeah, that's it. Thank you for listening.
Thanks, everyone.
Have a nice day.
I think we have time for maybe one quick question before the next talk begins. Oh, okay. We have a couple questions. So how do you erase processor fuses that are created not to be changed? So that's a great question. And in the OCP OSF checklist version 1, there's section 3, which talks about that in some detail. We need to encourage the processor vendors to allow multiple key slots, is basically what we're saying in that document. So that way it can revoke, like the first owner can write their key and then another owner can revoke that key.
We got another question. So how do you protect the core root of trust firmware from being replaced by an attacker? Yeah, that depends on which type of root of trust you're using. So you can use also, let's say, Intel TXT or Intel BootGuard or any other technology like flash write protection as root of trust for your firmware security. That depends on what you want to rely, and for sure, if you're having something like an OpenTitan or Microsoft Cerberus open source chip or open hardware chip with open source firmware on it for protection of the platform, that would be perfectly fine. So I think you can everything combined with open source firmware, even if that means sometimes you have to leave some open source components out of it. I hope that answers the question.
So I think the next talk is beginning, so let's all head over there. Okay, I think we're done with the live QA. Thank you.